these models are basically on this idea of a collective brain in cultural evolution. So the first is on this paradox of diversity. So it's this inherent trade-off that humans face thanks to specialization, which in turn affects the amount of cultural complexity that a society can maintain and the rates of innovation that it's capable of. So the thrust of the diversity, or the paradox of diversity, is that diversity is this fuel for innovation through recombination. So we only understand a sliver of our world, and often new ideas come about through the kinds of recombinations that take place at conferences like this. But by definition, diversity also divides us. So there's this coordination or communication trade-off that happens. For example, if we didn't speak the same language, it would be very difficult for me to convey all of this to you. So to resolve the paradox, we want to optimize on communication and coordination, but kind of retain other aspects of diversity. As I said, this is all new work and I haven't timed this, but I'm also hoping to discuss one related model on how the availability of resources and energy affect the scale of cooperation, giving us a kind of exogenous reason for the level of sociality that's needed for a collective brain to operate. Okay, so those are the things I'm talking about. So I've been watching a lot of the talks so far, and it's very interdisciplinary. People use models in all kinds of ways. So I just want to give you a quick bit of background on the way that I'll be using them, or people in cultural evolution tend to use them. So a lot of work in cultural evolution derives from evolutionary biology and population genetics, and they're really an extension of those models into the social and cultural world. So notably in a 1981 book by Cavalli, Schwartz, and Mark Feldman, and a 1985 book by Boyd and Richardson, Culture and the Evolutionary Process. And in the tradition of population genetics and the kind of messy world that is biology, these models are more ways to describe and explain underlying mechanics so that you can derive testable comparative statics. So how is one variable expected to change another? It's like an adjunct to thinking, just formally laying down what you think the logic of what's going on is. So, for example, in one classic model that kind of kickstarts this whole thing, Boyd and Richardson asked, under what conditions will natural selection select for an animal to pay attention to other members of its species, to other members of the group? And this is kind of the most basic requirement for cultural evolution and also for collective intelligence. You actually have to be learning from other members of the group. And they show that temporal variability is one way to achieve that. So you can play with these models if you want. This is a website we developed for an undergrad course I teach, but you can play with. We're going to talk about model 1 here. Okay. So for example, when the environment is very, very stable, let's zoom in a little bit. So when the environment is very, very stable, so that is the autocorrelation with the environment is close to 1, then genetic selection is really the answer, right? So skin color is an obvious example of that for humans. Latitude is a great predictor of UV radiation. You don't want to learn that individually. You should avoid the sun or get more of it. You don't want to learn it culturally. Genetic adaptation takes care of that for you. So you're optimizing vitamin D levels and avoiding skin cancer. And if the environment is highly unstable, you're down in this zone, you're basically doing a bunch of individual learning. So that's the blue, far away from any kind of social learning, because the information that you might be able to gather from other members of the group or from your genes are really out of date. And really, there's this kind of sweet spot, this red zone here, in which social learning and cultural learning win out. Okay. So in the same tradition, the collective brain derives from a model developed by Joe Henrich. We'll call it the Henrich transmission model. And he uses a standard formulation in this field, the Price equation, which is normally used to decompose evolution into within group selection and between group selection. But in this case, he wants to look at how selective transmission, so individuals learning from the best member of the group and their group, and incomplete inference from the environment affect the level of cultural complexity and innovation the society is able to maintain. So I'll give you the thrust of how this works. Actually, I'll give you the answer first. So what we find, or what the model predicts, is that there should be a relationship between sociality, which is effectively the number of learners and the number of teachers available, which is a function of a population size and connectivity. So you can see where we're heading toward the collective brain, and the level of cultural complexity and innovation that it's able to maintain. Now, we have all kinds of technologies that effectively enhance our sociality. So obviously video conferencing, but also writing and books and being able to record ideas beyond a lifetime. But basically, the idea is that if there is someone there's an amazing person in the population, an amazing hunter, let's say, and every little hunter wants to be like that person. That hunter is an amazing hunter for a reason, right? So most of the population, when they're trying to learn from that hunter, just aren't going to be as good. This is a Gumbel distribution, but it's robust to a normal distribution or other distributions too. So when a little hunter is trying to learn from that best hunter, the fact is that most of those students, most of your students, won't be as good as that amazing hunter. And the degree to which any of them are going to be as good or better is a function of transmission fidelity. So this alpha parameter here. So how able you are to convey the information, and of course that's under selection. We do a lot of work in figuring out how to transmit information better, as well as the diversity within the population. So as you increase the amount of diversity, you get more winners and losers. So you extend this tail, you're more likely to have at least one person to replace that great hunter. But at the same time, you also get this huge amount of inequality. A lot of individuals will not be as good because learning is lossy. So from this, you can derive. Again, this is just a straight up effect of the price equation. You can derive a relationship between the population size, the amount of diversity or the amount of variation in that population, and the transmission fidelity, going up with fidelity, obviously. And what you find is that as the number of skills or the complexity of those skills goes up, you need a higher effective population size in order to maintain this skill level, because you're always on this kind of treadmill. Every time, when a baby is born, it has to catch up on the last several thousand years of human history. And as things get more and more complicated, it takes longer and longer. So in some follow-up work to this, Alex Masudi, for example, points out that we don't learn any 20th century math. We're in the 21st century at the moment. We don't learn any 20th century math in high school, and often not in your undergraduate degree. So the world is becoming more and more complicated. This is too much to learn. Okay. There's a pile of work that's kind of shown this empirically, looked at it in terms of particular case studies as well as experimental work in a lab. Hidden in this is the paradox of diversity, and that's basically that this beta parameter here, this amount of variation, this diversity on the population, creates inequality, but also has the capacity for more innovation. You're going to get a few more people who are going to be as good or better than that hunter, but at the cost of everyone else, right? One way I sometimes like to think about this is that, we think about Silicon Valley as this amazing bastion of success. In reality, Silicon Valley is a graveyard of failure. It's just that the market is large enough that the few successes, the Apples, the Amazons, the Facebooks, pay for all of those failed innovations. And a lot of those entrepreneurs probably would have been better off with a salaried job. Okay, so in this new paper, we lay out a bunch of practical applied strategies for dealing with the paradox of diversity, the use of translators, in terms of cultural diversity, the use of existing populations that are partially acculturated, and so on. And we suggest that cultural evolvability is the correct framework for thinking about this problem. Evolvability in biology is not an organism's adaptedness to the current environment, but its ability to adapt to changing environments, which is going to be a function of things like diversity. If you don't have the diversity and the environment changes, you're screwed. But of course, that diversity means that you're not well adapted to the particular solution that a particular environment demands. You can read the paper for details, but what I want to focus on is just the formalization of this paradox of diversity that builds on the Henrich transmission model. So the basic idea is that we have a limited size brain. Let's just call it unit 1, and we can see in current medical data that human head sizes are under selection. So there is enough variation in the population that emergency birth intervention. So these are not planned cesareans, but an emergency cesarean, an emergency forceps use hockey sticks up with head size. The constraint is basically that a bigger brain lets you store and manage more information. You can read more about that in this paper, the cultural brain hypothesis. But it's really difficult to birth, and you have all kinds of issues to do with health and to do with oxygen and biome transfer and all that. So you have a fixed size brain. You have a population size n, just as we do in the Henrich model. But here, instead of just looking at the variation, we have multiple domains of knowledge that are needed for survival. So this is n, right? And there's going to be a certain number, a minimum threshold, the number of people needed per domain in order to just make it happen. So hunting a stag, for example, is going to require at least 3 people, let's say. Yeah. And there's going to be some amount of your brain space bounded between 0 and k that you need to dedicate to a domain in order for it to be successful. And of course, we have the scale of the population. And what we do is basically we have each person allocated to each person in our model is trying to spread out across these domains. So if you have not too many domains to learn, say there's 10 domains, you've got brain unit 1, and there isn't a very large population, you basically have to learn it all. But if you're in a very, this is the world of hunter-gatherers. I have to learn to build a house, and I have to learn to hunt, and I have to learn to protect myself. But if you're in a very large city, you can rely that there's enough other people in every other domain that you can specialize on this one little thing, right? And so from this, we can derive a relationship between cultural complexity, the size of the population, the number of domains, the minimum required, number of people, and minimum brain space required. And the first, almost sanity check is that what we find is that as population size grows, the number of domains that any person is required to learn in order to have a particular level of cultural complexity begins to decrease. In other words, if you're a doctor in a small town, you got to learn a lot of medicine. If you're a doctor in New York, you can specialize on a very small part of the renal system, and that's fine. There's plenty of other doctors to handle other things. And by corollary, of course, the number of domains known by each person will have to go up if there's more domains. So the next, we introduce this paradox. Domains are not independent of one another, right? They're related to each other. And if they truly were completely independent, so obviously language is one thing that binds us, but if they were truly independent, not only would we get super smart at one thing and stupid at everything else, but we wouldn't even be able to talk to each other. We wouldn't have a common language as we do at this conference to be able to converse about any of this. So to capture this, we use a formulation that's really been derived empirically from, or it's been used to measure social networks in other primates empirically. So we had some basis for thinking about it, which is some measure of network efficiency. And we allow our model to not just optimize on the level of innovation and cultural complexity, but also on the efficiency of the information transmission. So you don't want to be overconnected, you don't want to be underconnected, you want to be able to access that information easily. And this is a function of the overlap between domains. So if we all know the same domains, then you have a complete network. But if you know some domains and you've got some overlap with some other people and you've got some overlap with some other people, then you can eventually get this as close as you can to efficiency. And so what we find is that we're able to show this paradox of diversity as a framework. So there's going to be this trade-off between a population size, the diversity of the domains that they have, and this network efficiency parameter. Okay, that's great. I got through that very quickly. So in the next model, what we're interested in looking at is the paradox of diversity. It's nice that we were able to formalize it. It has some important implications for a wide variety of applied domains that I'm particularly interested in. But given that something has been driving up the level of cooperation in our population, and by corollary, violence seems to be declining overall, it might be nice to know what might be happening here. Because as population or sociality begins to grow, then innovation will naturally grow with it. And if something were to shrink our population suddenly, we would imagine that cultural complexity will fall with that, because the people who know all kinds of important things will disappear, especially in highly specialized domains. So again, I'm just assuming, I'm sorry that this is probably like really obvious to everyone here, but people are, when thinking about cooperation, people are very familiar with the prisoner's dilemma, where you have the choice between cooperating and getting a smaller sentence, or both defecting and getting a higher sentence. But if you defect and the other person cooperates, you get off scot-free. In a related game, the stag hunt game, also called the assurance game, there isn't just one Nash equilibrium, there's two. So you can either go and hunt hare by yourself, and regardless of whether the other person comes with you, you're going to get your hare. If they go hunting for hare, then they're going to get one too. But then there's also a cooperative strategy, which is that we might work together to get something a little bigger that increases both our payoff. So this is the prisoner's dilemma. But you can see here in the stag hunt, the key difference is that I'm going to get my stag anyway, but I could, if you agree to join me on a stag hunt, we could get a stag together. And you can adjust things like the risk of catching the stag and so on. But if you try to get a stag by yourself and the other person goes off and tries to get a hare, then you're going to be left with nothing, and the other person will have the hare. The stag hunt game is particularly useful for my purposes because I'm interested in the puzzle. We often talk about how cooperation is a big puzzle. It's actually not, in the sense that since 2005, Science Magazine said the puzzle of cooperation is one of the top 25 puzzles for the coming 25 years. Since then, and even before that, we actually understand a lot of the mechanisms that allow humans to cooperate. The puzzle is, how is it that we've ratcheted up so quickly? And why is it that the lower scales of cooperation that we see undermining higher scales, why don't they do that? Why has cooperation continued to rise? Because the thing that undermines cooperation is cooperation. So this is some of my work on corruption. So, for example, inclusive fitness helps explain why we cooperate with kin. Genes that can identify and favor copies of themselves will spread at the expense of genes that do not. Direct reciprocity, or reciprocal altruism, helps explain why you cooperate with your colleagues in the department, even if you don't like them, because quid pro quo, you scratch my back, I scratch yours, you steal my stuff, I steal yours, pure punishment. Indirect reciprocity, or reputation, helps explain why we cooperate with people we know of. So collaborators, invites to a conference, these are largely based on reputation. And of course, institutions. So instead of someone steals my stuff, depending on who they are and where they are, I might go after them. And in reality, I have a police force and judiciaries and the law to look after that. I pay my taxes for them. Very effective. But the trouble is, it gets undermined around the world, because when inclusive fitness undermines our institutions, that's nepotism. Or cronyism is, when direct reciprocity or indirect reciprocity, when a manager gives a job to their friend or a friend of a friend. It's one scale of cooperation undermining another. And we can capture that very nicely with this stag hunt game. So extending, for some background, there's a couple of review papers you might want to look at, but in terms of this model, we build on some earlier work looking at collective action in an n-person stag hunt game. So we don't just look at strategies between two individuals, but we include many individuals, as well as the competition that takes place when you're dividing up that stag. So that kind of this mix of cooperation and competition that's inherent in any of these kind of collective action games. So we extended to not only an in-person, but kind of an F stag hunt, if you like. So not only are there hares and stags, but there's bison and more, right? And you can coordinate on these higher scales. So in other words, you can work on a group, you can work on a project all by yourself. You can work on a project with a larger number of people. You can work on a very large project with hundreds of people. There's all kinds of important dynamics here. So for example, one of the questions that's important to understanding how these scales of cooperation undermine one another is, why would I work on a 100-person project rather than a single-person project? And the answer is effectively that, like the bison, there's something bigger that I can get by working with other people. And in order for that to be stable, that has to be bigger and better. My share of that has to be bigger and better than what I would get if I just worked by myself on something smaller. Okay. So in this setup, we basically build on these models for the defect and cooperation strategies, except that there are multiple stags in this game of different sizes defined by F. We have replicator dynamics that show which of these different strategies is going to dominate in any one of these games. I'm just going to jump to the answer, and the answer is that as long as there's overlap between these stags, as long as there's overlap between the resources and the energy that we're able to unlock by working together, then we're able to kind of use one level to achieve another. So in this paper, as well as the book that I'm working on, what I argue is that hunter-gatherers have been walking on fossil fuels as long as humans have been around, but they weren't able to access them, not only because of the technology, but also it requires a critical mass of people to dig up the oil and refine it and spread it to all the corners of the earth, right? There is always this potential, depending on the level of resources and energy that are available, for these lower scales to dominate. So in other words, there's always these eras of abundance and scarcity. As you kind of use things up, they get divided up. And these occur at multiple levels. So in our game, or in this model, what we find is that the utility goes up as long as there is something to unlock, right? Given the number of people, but that increases, I should have said this here, that increases the carrying capacity of the group, right? And as the group grows to meet that carrying capacity, the resources or energy per person shrinks, decreases. And only if there's the next level available to unlock will you continue doing this. So rather than kind of an overall decline in violence, our model would predict, or a rise in cooperation, our model would predict this kind of punctuated by these bouts of lower cooperation as we kind of transition between scarcity and abundance. Since I have 5 minutes, I'll mention one other thing that we're looking at is that the psychology of scarcity and the psychology of abundance are very, very different, right? So if the economy is booming and there's and somebody opens a coffee shop, that's a great sign for all of my cultural learning psychology to kick in. Like, I should open a coffee shop too. The coffee business is booming, right? That's the Silicon Valley mindset. But if you're in a constrained situation where there isn't enough resources to go around, funders' money has gone down, energy reserves, as here in Europe, have shrunk, and energy prices have gone up. There's less to go around, and suddenly another person opening a coffee shop is actually a signal that the only way for me to regain status is to make sure I harm their business. They've taken a piece of the market that I can never get back. So there's a very different psychology between kind of positive sum and zero sum environments. Okay, I think I'll leave it there.